All right, we are back with part 2 of 6.5, exponential functions. An exponential function has the form f of x equals c times a to the x power, where a is a positive real number but not 1, and c is any non-zero real number. All right, so let's just jump into an example. Let's just go ahead and jump right into an example since they gave us one anyway. It's not much to explain. Exponential functions are going to be graphed a little bit differently. We just finished talking about quadratics, which look like parabolas. And then now we are going to talk about exponential functions, which are going to look something like this, depending on which way it's going. All right, so draw the graph for each function. We have f of x equals 2 to the x power, and then we have g of x equals 1/2 to the x power. What I like about these are that they're fairly simple. It's a matter of plugging in one number to get out another number. Okay, they're functions. So we can look at our function table. Okay, and we could start off with any numbers. I usually do a couple of positive numbers every once in a while. You can start with couple positive, couple negatives. Doesn't really matter. You're just plugging in numbers to come up with, remember this x is your input, y is your output. So these are going to be the points that you can grab to form this graph for this function. So when x is 0, which means when this number is 0, what is my y value? Well, 2 to the 0 power is always going to give me 1. So I'm going to write this over here. That's going to give me 1. This means 2 to the first power, which is 2. This means 2 to the second power, which is 4. This means 2 to the third power. 2 to the third power, which is 8. So my points for this very first graph here can be 0, 1, 1, 2, 2, 4, and 3, 8. So I'm going to put those on my graph. 0, 1, when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. 1, 2, 3, 4. When x is 3, y is 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, the thing about exponential functions, it'll get close to touching the x-axis, but it won't touch it. Okay, so these lines, if I were to put some negative numbers in, I will be able to get some negative values. They will be fractions because they will keep getting closer and closer, but they won't touch it. So these lines kind of go like that. Okay, let's look at graphing another one. G of x equals 1/2 x. And this is where you'll see some fractions. Okay, once again, I'm going to put in 0, 1, 2, 3. And then I'm going to put 1/2 raised to the 0 power, which gives me 1. Then I have 1/2 raised to the first power. Which gives me 1/2. I'm going to write it as a decimal. Then I have 1/2 raised to the second power, which is 1/2 times 1/2, which is 1/4, which is 0.25. Then I have 1/2 raised to the third power, which is 1/2 times 1/2 times 1/2, which equals 1/8, 0.125. So my points are 0, 1, 1.5, 2.25, and 3, 1 point, oh, sorry, getting kind of tiny, 0.125. Okay, so I'm going to put those points on my graph. Okay, when x is 0, y is 1, same point here. When x is 1, y is 0.5, which is about right here, halfway. When x is 2, 1, 2, y is 0.25, which is a little bit closer. Notice it's getting closer and closer, and then 0.125 is little bit closer, but not on the line. So then I can draw my graph, goes up and goes this way without touching that, crossing that axis. Okay, so that's just a matter of plugging in inputs to get outputs. You don't really need any fancy formulas or steps or anything like that. Pick a couple of numbers as your input, and then your outputs will work out. All right, let's look at a application problem. Williams County was one of the fastest growing counties in America in 2015. One estimate of that growth uses this function here to model the population, where A is the population at the time of 0, and T is the time in years. According to the U.S. Census Bureau, the population was 22,398 in 2010. Use the model to find the population in 2015. All right, so first thing we need to know says AO is the population at time 0. So the population at, not at time, T equals 0. Right here, this is the population. And then the time, and T is time in years. So time in years in this case, if this was the population in 2010 and we want to find the population in 2015, we're looking at 5 years later. Okay, so it says use the model to find the population in 2015. I'm just going to plug in these numbers. I got A, which is my population, 22,398 times 1.095. That doesn't change. And then my time is 5 because it's 5 years between 2010 and 2015. So this was my at time 0, which is my starting time. And then we are looking for the population in 2015. Now it's just a matter of plugging that into my calculator. And it looks like my population in 2015 is about 35,259 people. So these problems, it's really just a matter of taking the formula that they give you and all the information that they give you and plugging it in, because they gave you everything that you needed here, from the population to the years. Okay. All right. Next up, we are moving into money, just slightly. Computing the value of an investment. Hold on, it's going too fast. Okay. All right, so we are going to talk about interest. Interest on a savings account can be compounded annually, semi-annually, quarterly, or daily. Just to kind of put it out there what this means. Annually is 1 year or 1 time per year. Semi-annually is 2 times per year. Quarterly, oh, I don't know why my pen is acting up. Quarterly is 4 times a year, and then daily would be every day, so 365 times a year. So where A is the amount of money, which includes the principal plus the earned interest, so this is called our future value. P is the principal amount initially invested. This is what we start with. That's our principal. R is the yearly rate. That's our rate, and it's in decimal form. Now remember, rate usually comes to us in percent, so we have to change it to a decimal. We'll get to that in a second. N is the number of times the interest is compounded per year, so that comes over here. And T is the time in years the principal has been invested. Okay. All right. So it says if $10,000 is invested at 8% per year compounded quarterly, find the value of the investment the amount, the future value, after 40 years. So let's start by writing down our key information here. Our principal is what we invest. That's our $10,000. Our rate is 8%, but we want to write that 8% as a decimal. 8% means 8 out of 100, which is 0.08. N is the number of times it's compounded. It says quarterly, so our N is 4. And T is the time, how long, is 40 years. Once again, we have everything we need to solve this problem. Now it is a matter of plugging it in and punching it into our calculator properly. So we're looking for our A. We have $10,000 as our P times 1 plus 0.08 over 4 times 4 times 40. I have no idea why my pen is not working properly. I apologize. Wasting time having to go back and rewrite it. Okay, so go ahead, take a second. My suggestion to you when you are typing this into your calculator, if you don't have a scientific calculator where you can use your parentheses and such, and you can see what you're typing in, I would do this first, then I would do this, and then I would rewrite it, and then solve it, because this, the only thing that's being raised to 160 is what's in the parentheses. So if you simplify what's in the parentheses first, let me go ahead and redo that so I can tell you exactly what it is. I will put in 0.08 divided by 4 first, and then put my 1 plus that, so that's 1.02 raised to the 160 power. So you can take your 1.02 and then you can raise that to your 160th power. Now my calculator is acting up. And then you will multiply that number by 10,000. Okay, so once you put all of that into your calculator, you should come out with $237,699.07. If you have your scientific calculator, you can punch that whole thing in with no problem. You will type in 10,000, put your parentheses, 1 plus 0.08 divided by this bar is your division bar, 4. Close your parentheses, and then you can use your little caret key to raise it to 160, or you can use your caret key and then put in parentheses 4 times 40. Okay, that's something that you will have to play with on your own, depending on your calculator. At least you know what the answer is you should get, so that as you play with it, you know what you're trying to come up with. All right, here's a reasonable question you might ask when investing in an account like the one in example 7. How long will you have to wait for the investment to grow to a certain amount? Being able to answer questions like this require a new function that allows us to solve equations where the variable time in this case is an exponent. In much the same way that we use roots to undo powers with solving equations, we can use a group of functions called logs to undo exponentials. Okay, so a log is what we're going to use to undo the exponents. And once again, this will make sense once we get into the example. Okay. All right. Here's a small example. Log of 2 times 2 to the x power equals x, because pretty much those cancel out. The log undoes the exponential, leaving the x unchanged. The fact that there are many different logs presents a problem when programming a calculator. You can't put infinitely many log buttons on a calculator. Most calculators have a button for log base 10, which is simply denoted with the word log. Fortunately, there's a formula that allows us to change the base of a log, and it's called the change of base formula. For any base b that is positive but not 1, the log function with base b denoted log b of x is a function with the following property here, okay? May sound like a bunch of mumble jumble, but it'll make sense when we start working out the problem. For any acceptable base b in any positive real numbers, we can use this as our change of base formula. So what's going to happen is we're going to take our problem and we'll plug it in and we'll divide log a. We'll have log a and log b. We'll divide those two to come up with a general number. So let's try it out. After being injured in an accident with a driver who was texting while driving, Maureen is awarded an $80,000 settlement. She wants to invest the money so that she has $100,000 to put toward a home. If the investment draws 6% interest compounded monthly, how long will it take her to reach her goal? So in this case, we are looking for time. My pen a second to catch up. In this case, we are looking for time. So we are going to use that same interest formula that we had earlier. A equals P times 1 plus R over N times NT. We're going to, on the side, write down the information we have. Our principal, which is what she's starting with, that's the $80,000. Our rate, which is 6%. Remember, we want to write that as a decimal. Our time is what we are looking for. Number of times compounded monthly, 12 times a year. And then we want our future value, which means our principal plus our interest, to equal $100,000. All right. So we're going to plug in what we have. Oh, this is crazy. $100,000 equals 80,000 times 1 plus 0.06 over 12 times 12t. So our goal is to get this t down so we can solve for t. That's our goal. Okay. The first thing we are going to want to do is we're going to want to simplify what's inside of these parentheses. Okay. And we have a lot of space, so I'm going to rewrite the problem. Now inside of my parentheses, I should have 1.005, and that's raised to the 12t. That is a parenthesis. Working to get t by itself. So I'm solving this just like I would a regular equation when I'm solving for a variable. My next step would be to divide by 80,000 on both sides. And that is to get rid of that over there, leaving me with 1.25 here. And that's a 12. It's not a bit 12. Let's see. I'll write that. 12t. Okay. At this point, I am going to take the log of both sides because I'm working on getting that 12t down. Okay. So to undo an exponent, I'm going to take the log of 1.005 on both sides. So I'm going to write log of 1.005, and that's going to be times 1.25 on this side equals the log of 1.005 on that side times what I have still written here. See if I put it on the charger for half a second. It's fully charged. That'll help it write better. I don't know. Okay, so when I take the log of both sides, that cancels that out, leaving me with log on that side, and that brings my 12t down. So it is no longer an exponent. It undoes the exponent. Now I have to use, now unless you have a calculator that you can type in log with a base of 1.005 times 125, you will have to use the change of base formula. Okay, so off to the side, we're going to use our change of base formula. Okay. Oops, sorry. Before we do that, we're trying to get the t by itself. Jumping the gun. We're trying to get the t by itself, so we want to divide both sides by 12 first. So we're left with t on that side. Now we're going to use our change of base formula, and we need to do the change of base formula for just this part. So we're going to, and I'm going to write it over here. That's our log A. And remember, you can scroll back up and look at the change of base formula. Our A will be this 1.25. So that's our log A divided by our log B, 1.005. I'm so sorry about this pencil, guys. I have no idea what's going on, but the video is almost over, so let's just keep going. So you can punch that in your calculator using your log button, okay? And you end up with 44.7. So now you can replace this with the 44.7 and divide it by 12. Okay, and we end up with 3.7. So it'll take about 3.7 years to reach, and all of that was done, to find the number of years it'll take to reach that $100,000 that Marine is trying to reach. All right, we just have one more example to do. One more example to do. Come on. Okay, right here. Carbon-14 is a radioactive isotope found in all living things. It begins to decay when an organism dies, and scientists can use the proportion remaining to estimate the age of objects derived from living matter, like bones, wooden tools, or textiles. Here's the function that we're going to use, and it describes the amount of carbon-14 in the sample, where A is the original amount, and X is the number of centuries, which means we're going by hundreds of years, since the carbon-14 began decaying. A wooden bowl is found at an archaeological dig in Peru. And when analyzed, it's found to have 62% of the amount of carbon found in a living sample. About how old is the bowl? Okay. All right. So now we are going, once again, we're going to use our the formula that they gave us. And obviously now we are looking for how old the bowl is. So we are looking at the X. So we're trying to get that X to come on down. All right. Hold on 1 second. All right. So let's do it. Let's plug in our numbers that we have 62%. So that's 62%. Oh, of the amount. So 62% of the amount of carbon found in a living sample of the type of wood. So because we're looking at that 62% of the amount of carbon-14, we are going to have to take 62%, turn it into a decimal, and that's going to be multiplied by that AO because that's the amount of carbon. Remember, that's the original amount. So we're looking for 62% of the original amount. And then that equals the original amount. And then I'm just rewriting the equation that they gave us. Minus negative 0.0175x. This pen is throwing me all off. It's frustrating me. Okay. All right, so 62% of the original amount, and we just said that AO is the original, and X is the number of centuries. Okay. All right, let's just try to get through this problem as it is the last problem. All right, so let's go ahead, and the first thing we want to do, okay, first thing we can do is get rid of this AO, the original amount, because it's on both sides, so we can cancel that out on both sides. We don't know the original amount, but we don't necessarily need it here. We're left with 0.62 equals 2 raised to the negative 0.0175x. Okay, and remember we're trying to get our x down. X is going to be how old the bowl is in centuries. So we're trying to get that x down. We're going to take the log of both sides. We can take the log 2 of both sides. To undo the exponent. That cancels those out, leaving us with log 2. That should be a little 2. So should that 0.62 equals negative 0.0175x. And then you have to use your change of base formula. And once you do that, you should end up with 39, about 39.4. Remember, we're talking about hundreds of centuries. Not hundreds of centuries. We're talking about centuries, which is 100 years. So we can multiply that by 100 to come out with 3,904. Oh my gosh, this is driving me nuts. 3,940 years. Okay, my pen's acting up. So, like I said, we did do one example where I showed you how to do the change of base formula. So that's what you will have to do here because you have to divide both sides by that. You have to use the change of base formula on just the numerator. That's log B divided by log A to come up with the number that you will divide by that negative 0.0175. Okay, so I'm going to go ahead and end the video here since my pen won't let us be great today. This is the answer you should get, 3,940. That should say years. And that's it. If you have any questions, I know this video was a little funky because I couldn't get my pen to write. So if there was anything that you did not understand because of it, please make sure that you are emailing me. I hope that you still got the gist of the lessons, even with the technical difficulties. I think you should be okay. Remember, on your homework, you can always hit show example, and it'll show you how to solve the same type of problem that you have.